P3, photons. This is an introduction to the rather strange idea that light, rather than being a nice smooth thing, actually arrives in lumps. So you're probably familiar with the electromagnetic spectrum. This idea that there are many waves on the spectrum, from radio waves right down here with long wavelengths all the way up through visible light to gamma radiation at the opposite end. And going from radio up to gamma, you have increasing energy. So the equation that we use for the whole of the spectrum is C equals F lambda. It's sometimes written as V equals F lambda, but certainly with the electromagnetic spectrum, all the waves travel at the speed of light. So, and the symbol for the speed of light is c, so we write it as C equals F lambda. And if you look on the formula sheet, you'll find that the speed of light is 3.0 times 10 to the 8 metres per second. So we use that a lot, and you do tend to remember it after a while, but it is on the formula sheet. The other thing to remember about electromagnetic waves is that they're transverse waves, so they wiggle up and down as they travel forward, so travelling in this direction. But they also have two components. They have an electric component, which in this diagram is going up and down, and a magnetic component, which is horizontal, so they're always at 90 degrees to each other. So it's quite an unusual waveform, but worth sort of recognising. Electromagnetic waves are emitted by charged particles when they lose energy, and there are various ways that they can lose energy. You could have a fast electron which is stopped or slowed down or changes direction. Any of those will cause it to lose energy. Or if the electron's in an atom, it could move from a shell, which you're probably familiar with the idea of shells in chemistry, down to a lower energy shell, and in doing that jump it emits some energy. So the energy we're talking about is associated with the electrons. Photon energy, we have an equation for, and the equation is E equals HF. So E for energy of the photon equals H, which is Planck's constant, times F, the frequency. Planck's constant is 6.63 times 10 to the minus 34 joule seconds. That, of course, is on the formula sheet. So you don't need to remember it, but you need to recognise it. Okay, so that's the equation, E equals HF. So from the starting point of waves, we have an equation that says C equals F lambda, and from the photon idea, we have another equation that says E equals HF, and they've both got a constant in them. So for the wave equation, we've got the speed of light is a constant. For the photon equation, we've got H, Planck's constant, is of course a constant. Both equations have got F in them, the frequency. So if you think about that, if you start off with the frequency, that from the wave equation gives you a particular wavelength, since C is constant, and from the photon equation, that means each photon at that frequency has a particular value of energy. So it has a wavelength, but it also has a fixed amount of energy. And when we talk about photons, we're talking about a little packet of energy.